This is Lab 3, Black Hole Orbit. The order of the presentation will be Introduction, which includes purpose, background information, and results, Explanation, which includes initial data and code overview, and finally the conclusion. The purpose of this lab was to create a computational model that models a star that is orbiting a black hole, then use the data file of the position versus time of the star that we were given and the information about the mass of the star and the black hole's position to make the code calculate the mass of the black hole. We know that momentum is equal to mass times velocity, that the circular motion involves both parallel and perpendicular components of the change of momentum, dp dt. We know the gravitational force equation, the magnitude, and we are to assume that the change in momentum, dp dt, is equal to the net force on the star, F net. Also, we know that the only force being exerted on the star is the gravitational force. So, the gravitational force is equal to our F net. Finally, we were able to create the code that calculated the right mass of the black hole, which was 3.566 e to the 31st kilograms. Now, the initial data that we were given were the star position versus time is all in the stardata.csv file. The star mass is 1.989 e to the 30th kilograms. The time step was 86,400 seconds, which is 1 day. The black hole position was 4 e to the 10th, negative 1 e 10th, 0 meters, and our initial time is equal to 0 seconds. Go ahead and look at the code. As stated before, here is the star's mass, and the origin, which is set to be the black hole's position, because it is the center of the orbit of the star, our gravitational constant, 6.7 e to the negative 11th, the time step, 86,400 seconds, and our initial time, which is t equals 0 seconds. So we find the change in velocity, we find the velocity by using the data file that we were given, and then use that velocity to find our initial and final momentum. We have to find the change in momentum and the change in velocity, and then we know that the delta dp dt is equal to our change in momentum over our change in time. As stated before, we are to assume that F net is equal to dp dt. This part of the code gives the direction of the motion of the star. So p hat is the unit vector of the parallel component of the change in momentum over time. So we find that unit vector, and then we find the magnitude of dp dt, which is just the magnitude of final momentum minus the magnitude of the initial momentum over the change in time, and then multiply that times p hat. And there we have dp dt parallel, which is equal to F net parallel. Then, by subtracting our general dp dt minus the dp dt parallel, we find dp dt perpendicular, which is equal to F net perpendicular. So, for our conclusion, we were asked to discuss how the perpendicular, parallel, and general net force are different from dp dt, delta p over delta t perpendicular, parallel, and general, how they are different. And what if the black hole was changed for another black hole, but the motion of the star was the same, and whether or not we were going to be able to tell the difference. So for the first question, if delta t tends to 0, then we can assume that they are the same, that delta p over delta t is equal to dp dt, and therefore the net force parallel, perpendicular, and general components are equal to the parallel, perpendicular, and general components of dp dt. So, in general, they are the same. What if? If the motion of the star is the same, and we have the same assumptions as before, we have no way of realizing the difference between the black holes, because the initial conditions are the same and all the assumptions are the same. And in general, when we have two objects, such as the star and the black hole, from which we know there is a gravitational force between them, we can use the movement of one of them with respect to the other one, and the mass of one of the two, and the change in momentum to calculate the net force and the components, and use all this to find the mass of the second object. That is how we were able to find the right mass of the black hole in this case. This is how we conclude Lab 3. Thanks for watching.